This is Qz19 Electrolysis. And for number one, the answer choice is B, in that electrolysis requires input of energy to drive chemical reactions. The other side of electrochemistry, of course, is the galvanic process, which are chemical reactions producing electrical energy. So you can summarize this in terms of energy or electrical energy produces chemical reactions, and in the galvanic process that we're going to talk about, chemical reactions produce electrical energy. So there is the dividing line. Now, in the analysis of electrical energy producing chemical reactions, this is a non-spontaneous process, and therefore delta G is positive in the free energy arena of thermodynamics. So you have to put energy into a system which has a positive delta G. On the other hand, the galvanic process is spontaneous, and this we'll see in our lecture. Delta G will be negative in that case, and we'll show you how to use that to predict standard cell potentials and non-standards. Anyway, okay. Chemical reaction at the cathode. Well, we're going to need a diagram here of the electrolytic process, and we have what is referred to as a battery jar, for lack of better terminology, and we'll work off of the melts electrolysis, and we'll say here's salt or ionic compound A, B, and of course this goes to liquid ions, cations of A plus anions of B, both in liquid state. So we have in the liquid melt electrodes that are connected to a power source, transformer, battery. Short side is negative side, and the long side is the positive side. So when we have cations in solution, they will be attracted to the negative pole, and anions attracted to the positive pole. I mean, it's just common sense here. Now, when this is attracted to this electrode, it undergoes a reduction, because of course the reduction process is a gain of electrons. So in this one, A plus an electron goes to the reduced form, and you'll hear that all day long when the galvanic work. Reduced form is kind of a phrase that I use, and most people in discussing electrochemistry will say, well, such as copper is in its reduced form at the cathode and places like that. But anyway, we'll get to that. On the other side, the excess electrons in the anion are attracted to the electrode that's on the plus side, and that one will undergo oxidation, usually with something like a halogen, and it will go to something B2. We have 2 of these plus a couple of electrons. So this is an oxidation process. So the electrode that is undergoing oxidation is what? Cathode or the anode? Anybody? Anode. Okay. So oxidation is the anode, anodic oxidation, and reduced side in the process going on at the reduction side is the cathode. So the terminology is based upon the chemistry, not the charge on the electrode. I'll say that again. The terminology of cathode is based upon the chemistry. In the galvanic work, you'll find out the electrode, while in negative in electrolysis, will be a positive in the galvanic. But it's still, the oxidation will take place, and you'll see, and we'll call it the cathode. And on the other side, oxidation is the anode, sorry, and then reduction is the cathode. But it'll be opposite charges to what you see in the electrolytic cell. So reaction at the cathode is B choice in here, reduction. And the anode is the oxidation. Okay. Electrolysis of sodium chloride. Cl minus. So again, we draw the electrolytic cell and hook it up to our battery. Minus. So sodium will go to the negative electrode, which is connected to the negative pole, and chloride will go to the positive pole. Now sodium undergoes reduction, electron going to sodium, and chloride will undergo oxidation, chlorine plus a couple of electrons. We're going to add these together to get the net cell reaction. We have to double this one, and so that the charges will drop out. So, and the reduction is the cathode side, as we talked about a moment ago, and the anodic side is the oxidation side. That's for the chloride. So this is oxidation, anode, and reduction, the cathode. Okay. All right. Then we can add these together. 2 sodiums plus 2 chlorides in the melt will go to chlorine gas plus 2 sodium in basic standard states. The electrolytic process always drives the reaction, and the products will be elements in basic standard state. That is, you'll find these with a delta HF with a value of 0 in the back of the book. Okay, so for these, delta HF becomes 0 in the standard state form. Associated with the electrolytic process is delta G greater than 0. What does that mean? It means it's non-spontaneous. And what does that mean? It means that the process to operate requires the input of outside energy source. Requires input of energy. So this would be energy giving us chemical reactions. And so when we do the galvanic process, that will be opposite. We will find the chemical reactions will be producing the electrical energy. Car batteries operate on the galvanic voltaic principles. So, greater than 0, A choice. What if delta G is equal to 0? What kind of condition does that define? Anybody?
Equilibrium?
That's right. Now we'll look at that in the galvanic process in terms of what we call a standard, determining standard cells. And we can use electrochemistry to define equilibrium constants. So keep that in mind as we get into galvanics. You'll see that pop up again, and we'll use it to determine equilibrium constants using galvanic cells. We'll show you when the time comes. Finally, number 5, I gave you some aqueous reactions, and well, I can put this up here. So in the cathodic reactions, the possibilities for copper and bromide, well, copper would undergo reduction and the bromide would undergo oxidation. Well, how would I know that? How would I know that copper undergoes reduction and bromide undergoes the oxidation process? Well, I'll look on the activities here. Well, bromine's not on here. I'll go to the, probably can't, I may have it up here. Let me see. D choice. Copper undergoes the reduction to copper solid. Bromide undergoes oxidation to bromine plus 2 electrons like that. Add them together, we have electrons drop out, and so that's copper plus a couple of bromides going to Er2, standard state, copper, and standard state. So this is the reduced form of copper, and this is the oxidation of bromide in the order given. So these two are the dominant reactions in a aqueous electrolysis.